Alright, so I'm actually using the end of the cutting tool as a probe, believe it or not. And I'm using the copper. Okay, I've got the ground connected here with just a piece of tape. I've got it running over here, obviously, to the ground on the duet. And then I've got an alligator clip right there, as you can see. And that guy runs up here, and it's connected to a 3 mega ohm pull-up resistor, and then that guy runs all the way back, obviously, through the channel back down here to the input on the board. And I'm actually using the cutting tool as the most precise measuring. Now I've actually got up here, I've got one that's just a point, and I usually just use it because it's better, because this thing actually has 2 flutes on it. But the idea here is to actually use the actual end, I don't know if I can get a focus, the actual end of the tool. It is not focusing. The actual end of the tool as the probe. I thought I could get a good resistance through the whole unit and just ground the whole unit, but I don't think it likes that black oxidized coating on the chuck or the collet. So here we are in Fusion, and in here I designed the model. Let's see, that one's not supposed to be in there. So there's a connection that holds it on the shaft, and then this whole top plate is the PCB. I'm using the double thick PCB, but it's only got 1 ounce copper on it, so I need to find some better. This is the stuff I bought at Apex a long time ago for 20 bucks, so I'm gonna use it. So basically I've got my part, and I'm only going to machine that part. I 3D printed the other parts. Matter of fact, there's one right there. So if you look here, we're going to go to the cam, and I've already got these cammed up. So I'm going to be drilling the holes. I'm going to be machining these slots, and I'm going to actually hand cut the little connectors right there because I want it to be smooth. So I'm going to hand cut that and peel those off. And then I've got the holes in the middle and the outside of the board, then the inside last in case this comes loose. I already did a test piece right there, and the inside came loose, and I had to stop it. So lesson learned. The tape didn't hold it down well enough. I've actually got double-sided sticky tape holding this down, but I'm going to tape the corners because they're not going to be machined anyway. So I got to really make sure that thing stays in place. Now the trick with this is if you go in here to post processor. Okay, I actually made a post-processor for Fusion. This has actually been a very long process. I've been wanting to do this for quite a very long time for my 3D printers, and especially for the Duet. Now, somebody has already created one for Marlin firmware, and I think it uses a fan output. And that's it. It's pretty simple. So actually what I did is I grabbed his original file, or their original file, which they've got some notes here in this file, and I actually grabbed it and I edited in the other things that I wanted to do. So all this stuff here, I had to go in and edit the post processor and stick in the proper lines of code so that it's sput out, is that a word? So it's spit out the proper G-code format to turn on and off my my unit, because I'm using the servo option pulse width modulated outputs. So in Fusion, the difference between what I'm doing, if I go in here and edit, I go in here and I look at the spindle RPM. This says 70 RPM, but actually what that is if you go in and look at the file, it's the S value, and the S value is the pulse width modulated output frequency, or actually the pulse width that goes out in the channel I want it to, according to the output there, the M280. So I made a video a long time ago on how I connected this guy, but the RWG OSD is connected to a servo output, which I built a chip for, and then right here, that's the control board for the brushless motor, and then I made this spindle. So if you've never seen that, there's a whole bunch of videos on that, so you guys can go check it out if you want. But yeah, so basically I exported the the G-code via the post processor from Fusion, and I have loaded it into my Duet Wi-Fi. And there it is. There's the basically this is the copper clad board, so you can see how it auto leveled the copper clad board, which is awesome. So it knows the surface a lot better than I do, because it's not really truly flat. So I'm just going to drop it on here, and we're going to try to cut this thing out. I've got different tools here. The ones I'm actually going to be using looks like this. It's a in-mill cutter. Actually don't even know, what is it? It's a .0625 inch, 1.59 millimeter. And then I've got these other type of cutters. I'm not going to use these in this time. This is for cutting the slots that I told you I was going to do by hand. And then here are these the drill bits. So this is just a set of drill bits I'm going to be drilling those holes with. So right now I got this blank copper clad, only one side. The other side I peeled off, even though it did originally have it. I peeled it off because I didn't want the interference from arcing. And now we're going to fire this thing up and do some time lapse. Well then, after a few beginning catastrophes, we did actually get it done here. So the center, I actually left it off. And I left it off because I didn't cut all the way through, because I didn't want it to fall out. Last time I tried this with the sample piece, it did not work very well. So let's just see if we can pop this board out. Yeah, just where I wanted it. Almost through. Oh, that's pretty. Okay. Well, there it is. And now we're going to finish that center hole by hand and mount it on the motor here. I'm going to use a piece of strip. Printed it out to scale there so I could try to get stuff matched up here and make up the brush holder. So I'm going to use some contacts from Relays. Little button cells should work pretty well for contacts. So we'll get that all figured out and show you what it looks like. Alrighty then. There it is. The screw hole pattern mounted up perfectly. A little too close to the magnet there. It's acting funny on my camera again. It looks really good. It's nice and round. It is also pretty nice and square. So the next part of the process is to understand how I'm going to connect the brushes. I'm going to take this piece and mount it like this. And then the brushes are all going to be on one side, and I'm going to put the power out of the bottom, and I'll put the coil terminals out of the top. And that's just a piece of printed circuit board. Good footage here, huh? So I'm going to connect the commutator like this, from the inside to the outside of this side, from the inside to the inside of this side, and then the reverse polarity there. Then these get shorted out here and here. And that's easy to do since I put all these extra tabs and solder joints on there. So this should work just fine. I'm not 100% sure how well these brushes are going to rub on there. If I had some sort of a conductive grease, that would probably be perfectly fine, but I don't know if that's what I really want, because I kind of want the bad contact in the arcing. So we'll see. Might have to get some carbon brushes and make those up. So either way, I'm going to make this by hand. I'm just going to take a knife and I'm going to scar the copper to match what I got here. So I'm just going to scar the copper and peel it off. I'll get some shots of that. And then we'll solder the brush holders on there so we can just replace them whenever we want to switch out the brushes. And then when we want to switch out the type of directions here, we can do that. We also have to do the brakes in here. We'll do that too. Okay, so here's my original drawing. You can see I've got these splices here. So instead of machining those, what I did is I took a fine grit disc here. I think I've even got a finer one that would probably be better. And I just did it manually with the Dremel. And I did that because I wanted it to be a smooth transition. And so I figured doing it by hand instead of milling it would be better. Now, obviously, if I etch this, it will be better. So next time I can etch it, and then it'll have a smooth edge on it. And then I can also just CNC the circle and then etch the board. I don't have the stuff I need to etch this right now, and I wanted to get it done, so I did it through CNC. And then the long board, this guy, I again did the same thing. Now, you can see I took the Dremel and did these edges. If you're wondering why, it's because if I use high voltage, it will leak out any place that there's a sharp edge. So I tried to get rid of most of the sharp edges. So this thing will sit like this, and then there'll be a brush contact here, 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 and here, and I'm going to figure out the best way to do that. I got this little contact, which seems to be the best option because it's got a little bit of a fat rounded edge on it. And we'll just give that a shot for a while, and if I don't like it, I'll get some brushes, but the carbon will make it run smooth, but it'll also get in everywhere. So we'll just see how it goes, but now we got to put that on there. So the idea here is to be able to take that disc off, switch the angle of commutation, and then be able to make new discs for that and use the same setup. So yeah, I think that's pretty swell. Got a little gap in there. It's nice and round, nice and square. 5-point mounting hole. This is a really thick fiberglass, but it's not thick copper. It's only 1 ounce, so not really sure how long it'll last. If I don't put any lubricant on it, it might start burning the edges, but that's a chance that I'm willing to take because this is just a test configuration. It's 110 degrees on, 35 shorted, 35 off, 110 on, 35 shorted, 35 off, with of course a little gap, so it's a little less than that. Realistically, I believe I'm going to end up with a 45-degree angle, which was our first thought. However, during our testing, we realized that the maximum point where we could get power out was during 110 degrees, actually a little bit over that. So I shortened it, but 45 is, I don't know. Not sure if that's the right, but experimentally this shows us that about 110 is a good place to start. So we'll start there. Let's get the brushes put on. Okay, it's a new day. Got all the brush contacts on there. I cannot get too close, so we're going to have some problems. But you can see my solder joints right here. So on the back side, there are the wires. You can't see them, but I got them on the back. And basically, that allows us to connect each thing on each one, depending on my schematic, of which I put right there. So now it's time to connect all this up and see what our signals look like. Alright, we are running. Bad contrast again. So, scope shot, I paused it already. Looks about like this. So you can see that dip. That's induced voltage and current. That's a dip in current, that's a rise in voltage. It's not above the battery line, but that's okay. The peak-to-peak voltage of the ring is, well, here it's only 9.6, but sometimes it's up over 13,000 volts. Not too shabby. Right now it's optimized for maximum induction. Let me show you what it looks like at not maximized induction. Right now we're running at somewhere around 260 RPM. So let me configure it differently. Alright, you can see here that's about where it switches on, considering where the magnet is at. Remember, there's no shorts right now. And that's about where it switches off. So it's optimized for basically maximum induction between here and here. So now what I'm going to do is maximize it for RPM. Alright, now we're running at maximum RPM. You can see what the scope shot looks like here. Well, actually, this negative dip is induction. So the battery voltage starts to come up before it shuts off. That's actually induction. So let me shut it off here and I'll show you what it actually looks like. So interestingly enough, it's actually turning on way back here. So it fires here and it's trying to spin this way. So if you just let it sit here, it'll actually go reverse. So this whole cycle's on and it shuts off about mid-center. So that's maximum RPM, but does not give us much induction.